see them every now and again.
Should we wait for a present?
Oh, all the way back here. But when we stopped at,
It's not there, I mean, it went straight across.
yeah, and like when we stopped at I think it was the first overlook, there were like 3 or 4 of them in a parallel line, heading off into the distance. And I'm just like, how does it do that one, and what is it?
It'd be weird to see geomorphology, or like geomorph here, because like it's...
Yeah, that's what I was saying. Everything's horizontal
Cut
except for
straight
these
from
weird little intrusions.
Well, we take some.
Yeah.
Does it continue up?
Well, yeah, it does. Look, there's more of this. This one's one straight line. Look, I don't know if it's the same thing, but you can see lines with the rock.
It's so sad.
Oh, look at that. Another picture of each one. And then Jake is going to do whatever Jake does. That's himself. Wow. There's a special type of weathering you can see when you get to here. It's called popcorn weathering. It looks kind of like that. It's just like it's too bad. Looks like popcorn. So, kind of see how it looks kind of like that in there. Like the real bumpy.
Yeah.
Like too wet. Yeah, as it dries out, it forms those patterns. Okay, so what you want to do is you're going to want to get a squirrel suit and just go.
They should definitely.
You need like a sled.
Oh, Sasquatch homes.
Oh look, somebody dropped a... Is that a GoPro or is that just like a walking stick?
I don't want to get a picture of her.
Oh, no. Yeah, no. I think that's like a selfie stick.
Yeah.
Go down on the spot.
Look down. Is there actually cars closing?
Yeah. Interesting.
Stay here long enough, you can hear them calling out.
Wonder if it's...
I thought they lived in the woods.
That's where the bridge is.
Oh, yeah. What type of Sasquatch?
The ridge one.
Ridge Sasquatch? Ridge. Oh. Yeah, those are like slums.
There's actually a Sasquatch economy.
I didn't know this. Yeah, like a hierarchy.
Oh, someone's getting pulled over.
Oh, wow.
Oh, dang.
Sasquatch.
That's tragic.
Sasquatch.
You're going to tell us what the vertical intrusions are? We're going to see a town.
You guys actually do know?
No?
Well, we know because he accidentally did it.
Throw under the bus.
That was okay.
You're messed up for that.
I just don't understand them.
Okay.
I'll talk about it after.
All right, Talon, you want to
Give us your wisdom.
I can try.
Alright,
Okay.
You said the spot I already wiped off.
Should we like start whenever? Are you taking a picture of me?
No.
Okay. The geologic features here give us a look into the Earth history and the Badland layers, and they're known for the colorful rock formations, deep canyons, and towering spires that you see. It is located in southwestern South Dakota, near the city of Wall. It is sedimentary rocks, which were deposited 28 to 75 million years ago. They were deposited by shallow seas, rivers, and wind. They consist of sandstone, siltstone, mudstone, limestone, shale, and volcanic ash. The ash comes from an eruption that occurred in the Great Basin near modern-day Nevada and Utah. Due to the lithification, where sediments are turned to solid rock, volcanic ash was turned to the color beige. Only one layer of pure ash still exists within the layers, and the others have eroded by about 50%. This layer is called the Rockeford ash. Along with the deposition, tectonic forces form the Badlands. About 5 million years ago, tectonic plates shifted the rock strata through uplift and folding forces. The rock layers are moderately soft, so they are prone to erosion, which is occurring about 1 inch per year, and it is said that the Badlands may erode within the next 500,000 years. The base formation is the Pierce Shale, with the top layers being the Sharps Formation, which was deposited about 28 million years ago. The erosion began around 500,000 years ago due to the Cheyenne and White rivers flowing through the landscape. The rivers caused the canyons, narrow channels, and rough peaks seen today. The Badlands in general is a geologic term for soft sediments prone to erosion by wind and water. And the Pierce Shale is the oldest of the layers. It was deposited around 75 to 69 million years ago. It was deposited by the inland sea known as the Western Interior Seaway. The seaway ranged from the Gulf of Mexico to the Arctic Ocean, covering the Great Plains and warm, shallow water. The marine life can be dated to the time of the dinosaurs, but no dinosaur remains have been found here due to the fact that most couldn't swim. Ammonites and baculites are common fossils in the Pierce Shale, confirming the marine environment. The yellow mounds are what lay on top of the Pierce Shale. They are very similar to the base layer, but look very different. After the seaway drained from the uplift of the Black Hills and Rocky Mountains, the leftover ocean mud weathered down into the soils and preserved them as the yellow mounds. This is called a paleosoil, which is the ancient fossilized soils preserved in the rock record. They're often seen as the brightly colored layers. The mounds get their yellow color from the mineral goethite, which is found in soil and in low temperature environments. And next is the Chadron Formation, which consists of claystone beds that appear light gray. These were deposited around 37 to 34 million years ago in the ancient floodplains. Every time the rivers flooded, a new layer was deposited on the land. The environment at the time was hot and wet, so around 34 to 30 million years ago during the Oligocene, it was a cooler and drier time, which is when the Brule Formation formed. At the time, mammals dominated the environment. The hot and wet environment turned into a savanna. Due to this, now only a few rivers flowed through the Badlands from the Black Hills. The Rockefort ash is the base layer of the next layer, which is the Sharps Formation. It is the boundary between the Sharps and Brule, and it was formed around 30 to 28 billion years ago and is the youngest formation. Most of the Sharps Formation is sandstone due to the rivers as the climate began to cool and dry. And the Brule and Sharps Formation are what create the rugged peaks and canyons. And the Badlands are deep-rooted in human terms, but on the time scale are very shallow. There is constant and ongoing erosion occurring. And as the erosion occurs, sediments wash into the White, Cheyenne, and Bad rivers that flow into the Missouri and Mississippi that can carry sediments as far as the Gulf of Mexico now. Due to the climate, erosion occurs easily. The wind, rain, freeze, and thaw action that occurs has worn down the sediments and created the Badlands Wall. This wall surrounds most of the Badlands, and this is where the town nearby is named Wall because the wall dominates the horizon. And the Badlands did not become a national park until Congress voted in favor of it in 1978. It became a national park to preserve and protect the fossils, plants, rocks, and animals that were being exploited by collectors all the way up until 1978. One unique feature that is seen all across the Badlands is the hoodoos, which are the tall spires that are caused by erosion. Not only is there geologic history within the Badlands, but there's human history as well, specifically Native American history. The DOS Act was passed in 1887 when President Cleveland was in office. It stated that the federal government was allowed to break up tribal lands, and the government wanted to integrate tribes into American society through agriculture, so they were aiming to divide the lands into individual plots. The only natives allowed to become citizens at the time were those that accepted the act and gave up their land. The outcome was not the original idea. Ultimately, the government took and sold 90 million acres to non-native U.S. citizens, and the land was allotted to the natives was often unfit for farming, less than they were told it would be, and or land they had already owned. And then the tribes were not adequately paid or given land sufficient to survive on. The Badlands were part of this land given to the natives that you can see is not fertile for farming and would be challenging to live off of. Overall, the Badlands National Park was incredibly diverse and fascinating geological and human history. ranging from the ancient seaway to grasslands to the rock formations, fossils, and erosion. These all offer a chance to explore millions of years of geological and earth history within the layers of the colorful sediments, vast canyons, and towering spires.
Those of you that have had, how many have had mineralogy? Okay, what is goethite? How do you pronounce it?
Go tight.
Goethite? Geothite?
Nobody here in Cal has had it.
Gurtite.
Oh.
It's pronounced. Yeah, it's spelled G-O-E-T-H-I-T. There's no E, or there's no R in it, but it's pronounced gurtite.
Okay.
So those of you that will take mineralogy, when you see it, you'll know why she said goethite, but it's gurtite.
Oligocene.
And oligocene, not oligocene.
That was always
Which
said.
you've had historical, so I'm gonna let that go for now. Here, let's come over this way. Talon mentioned hoodoos, and Bryce Canyon National Park is known for hoodoos. And what's different about what you see here versus Bryce is there are hoodoos here, but they're kind of few and far between. But you do get those like sharp pinnacles. But I will show you. Yeah, there was right there. Yeah. That would be a hoodoo. A hoodoo technically has a resistant block, and then the stuff underneath it is eroding more easily. And so that resistant block at the top, or a resistant layer that is breaking into blocks, is kind of protecting the stuff underneath it. And then eventually it gets too skinny, like you see right here, and then that resistant block just tumbles down. And so if you look up there, that block on that hoodoo, you can trace it along to that layer. And notice how it's kind of undercut. Eventually, that really loose shaly stuff underneath will erode and those blocks will tumble down. But that's a hoodoo. Mostly, it's the lower stuff is so easily erodible that they don't last very long here.
You have vertical, like cylindrical shapes beneath the capstone as opposed to like these more round or slopey things.
It's really, like you can see, there's a really good example right there. So as the cracks, the vertical cracks are exploited, then the blocks drop down. So you end up, like if you see this line of peaks, imagine each one of those capped with a block, you know, all at the same height, and then eventually it wears away. You can probably even figure what unit was protecting it. But so anyway, that's that. I do want to real quickly make sure everybody's on the same page for geologic time. So what era are we in here?
Cenozoic.
Good, we're in the Cenozoic. And we're going to be mapping in the Yellow Mounds, which is the Pier Formation. That is Mesozoic. So we are going to be standing on, it's not the KT boundary because the boundary isn't there. It's been eroded away, but we'll be standing on time spanning from the Mesozoic to the Cenozoic. So there are not, there aren't Paleocene sediments here in the park. We go right from the Pierre Shale, P-I-E-R-R-E, named after Pierre, North Dakota, not Pierre. And the Pierre Shale and the Mancos Shale, which we will see in Utah, are the same. They are both part of the Cretaceous Seaway. So they were deposited in the Cretaceous. They are kind of organic and iron-rich shales. They're generally black to gray. So if you notice the shaly stuff as we were driving in yesterday, the hillsides were a real dark gray. That was Pierre Shale. But it weathers because it's got iron in the shale, it weathers to yellowish color goethite. And then there is a paleosol that is the top of the pier formation, and that we'll definitely see. You'll see, so it's going to be like yellow, red, and then Shadron when we get to the map area. So the Shadron is kind of Eocene, very late Eocene to Oligocene. Okay, so let's real quickly make sure everybody knows what they're talking about here. So this is the Mesozoic and the Cenozoic. So I've got the era on this side. So what period is this?
Cretaceous?
Cretaceous. Okay, so that's the Cretaceous. That line is what?
KT?
KT boundary. So what's the age?
66 million.
Yep, 66. Then what? What period?
Paleogene?
I will accept tertiary, but only because I haven't had you in class. So for those of you that haven't had historical, we don't really use tertiary anymore. I mean, it's still in all the literature, but it's an antiquated term. And if you don't know why, ask me later, because it's kind of a funny story. It's now broken into two periods. The tertiary is now two periods. So what are the two periods? Paleogene and Neogene. Paleo for ancient, Neo for new. So Paleogene is the period, Paleocene is the epoch. Okay, so when does the Paleocene end?
56 million.
Good, 56 million years ago. Then we get into the
Eocene.
Eocene. And when does the Eocene end?
33.9.
33.9. Rock on Milwaukee. Okay. What comes after the Eocene? The
Oligocene?
Oligocene. The Oligocene, and that ends when? 23. Okay. Miocene. Okay, and that ends when?
5.6?
5.6. And then Pliocene. The Pliocene is good, 2.3. And then the Pleistocene. Pleistocene ends at 0.01. And I can't even fit it in there. What comes after that? The Holocene. Yeah. So the Pleistocene is 2.3 million years ago. The start of the major ice age, ending about 10,000 years ago with the Holocene. We're not going to talk about the Anthropocene. So this is the Cenozoic broken up into epochs. Okay, we are basically like here, right? And then there is Miocene and Pliocene, and we actually saw some evidence of that, but you didn't. I did, because I know what to look for. But there are some gravels. So that's the time scale here. Okay. Now, in terms of climate, the Eocene was pretty wet, and so a lot of what would have been deposited as the mountains were rising to the west from the Laramide orogeny, which put a pin in that. We'll talk about that tomorrow. But just remember, the land to the west was rising. As that was happening, there were pretty vigorous streams throughout this area, and the area was rising. So what's happening?
Erosion.
Yeah, erosion, and because there was a lot of water available, and it was vigorous erosion and water carrying sediment, it pretty much like washed stuff away. Yeah. So the as it's eroding, that's why we don't see much during the Eocene here. Okay, because we had relatively significant uplift as the, think about if this is west and my elbow is east, the mountains over there are rising up, so the land is doing this. And it's wet, so you have it's all being kind of shed. Then things slow down, tectonically, things slow down, and the climate dries considerably. We get to arid, not so much arid, it's kind of like semi-arid to prairie grassland into the Oligocene, and we have kind of discontinuous. So we talked about lateral continuity. Lateral continuity is a really generic term, meaning things are deposited over large areas. But think about a delta. A delta has all of these channels cut into the sands and gravels, and then there's like channel switching and things going on all the time. Even daily channels are switching. You have lobe switching going on the scale of decades and centuries. It still is laterally continuous, but locally it's, from here to there, it might be I'm standing in a stream channel and that's the shore. That's what we see in a lot of the Oligocene, is these kind of isolated, like maybe some pools, but it's mostly this kind of dry area, wind-blown sediments, a little bit of, during rain events, you might have ephemeral streams carrying sediment and then drying up, and you have these ephemeral pools that dry up. Those ephemeral pools oftentimes would do what? As they dried up, what would happen to what's in the pools? What kinds of sediments? Mud and? Well, that's part of mud.
Salt?
That's part of mud. Think chemically.
Salts?
Yeah. Salts aren't just NaCl. In fact, it's a small component, calcium carbonate. So there's some limestones in here that are actually representing these flats that filled up in the wet times, and then they would slowly evaporate. And so if you know anything about evaporative deposition in desert environments, what is the most soluble of the natural common salts? Most soluble. Yeah. That's not a salt. A salt is just a metal and a non-metal. What's your favorite salt?
Sodium chloride.
Sodium chloride, yeah. It's your favorite because you can eat it, because your body can really easily split it apart. So if it very easily dissolves, it also very easily precipitates. So salt, NaCl, precipitates quickly. Okay. What's another salt that would precipitate from natural waters? What's that? That's you're close. That's part of it. Yeah, potassium chloride, which is sylvite. That's another one. Good. What's another one?
Magnesium chloride.
Now you're just throwing out chlorides. Magnesium chloride, zirconium chloride. That sounds good. Gypsum and calcium carbonate. Yeah, gypsum and calcium carbonate. So calcium carbonate is calcium and then carbonate CO3. So the CO3 is the nonmetal. We call that an anionic complex. Gypsum is calcium sulfate.
Water.
Yeah, it's hydrated calcium sulfate, SO4. So it is, SO4 is the anionic complex. So your salt is metal, calcium, nonmetal, sulfate. Metal, calcium, nonmetal, carbonate. Metal, sodium, nonmetal, chlorine, and of course sylvite. Okay,
Metals
so
being from the first two columns.
yeah. So think about what that means in terms of solubility. As things are drying out, you get sodium chloride precipitating, and then you might get gypsum precipitating and calcium carbonate precipitating. So we get these little limestone lenses. So today I want you to kind of note where you might see these thin to thickening to thinning layers that look kind of roundy in their erosional profile. That's a very technical term, roundy, because it's limestone, so it weathers, it dissolves. So do you see any kind of semi to discontinuous roundy layers?
Like
gravel?
right,
Would the limestone layers be more resistant or less resistant than the wind-blown silts and fines? More resistant, yeah, so they're going to stick out. Yeah, you see those are limestone layers, and then the reds and the tans. So the white up there, yeah, that's what's capping that hoodoo right there, okay? So when you're looking at the sediment, and this is why Griswoldian visitors to the national parks always drive me crazy, because they look at it and they're like, oh, that's pretty, and then they walk away. As a geologist, I come up here and I'm like, oh my God, where I'm standing was this environment with all of this stuff happening, and then now it's flooded, and after a really big storm, there's a giant pool here, and it's evaporating slowly over time, and there's little maybe tadpole-like organisms in it, or there's crocodiles that live in these shallow streams, and maybe some large mammals that come and drink in these pools, and some of them fight and die, and they are left behind as fossils. Okay? You guys know what Griswoldian means?
Yeah.
Yeah, right.
Yeah, so if you guys have seen Vacation, National Lampoon's Vacation, they get to the Grand Canyon, they walk up to the overlook and go, and then leave. That's Griswoldian visitation. So that's like I think about national parks in a completely different way, because the more you know. All right, so the last thing I wanted to mention here is based on your question. Okay, so at the last site. Okay, so we have these. Have a bench here. So this, we're going to just call this north. So there's a little kind of one of these straight cliffs. All right, and it rains, and the water lands up here, and it lands down here, and the water kind of falls over, and it flows down, right? So this is north. We're looking down on this kind of cliff. So this is grassy, and then this is like a slump block. Oh, there's actually two things I want to see. Okay, so that's exposed soft sediment. You guys see that? Okay, so what is going to happen where the water kind of spills over that edge?
To the down cut?
It's gonna cut down, and so it's gonna kind of do this, right? And maybe this stuff is biting down, and another little slump block forms there. Okay. And now the next time it rains, the water focuses, right? It's going to focus in here. Maybe get a little bit there. Okay, and it just keeps doing that.
Yeah.
And it just keeps doing this. Oops. Okay. So it's eroding back into that cliff. What do we call that? It's not, it could be undercutting. It could be undercutting. Undercutting is one way that it happens. What's that?
Something erosion. Water erosion.
It's really easy. Don't overthink it.
Water erosion.
No, it's not that easy.
That's what I
Headward erosion, right? Because this is the head of the channel, so it's slowly eating back. It can happen in a few different ways. Headward erosion of streams, that's how streams grow, right? They get longer. They are cutting down if there's uplift. They're cutting down, or if they're high gradient, but they also get longer over time. That's how the Appalachians got so small after being like the Himalayas.
Yeah.
Okay, so you erode back. That's headward erosion, and it is occurring as this kind of eats back into these soft sediments. It can happen due to undercutting, so maybe it flows over that grassy stuff, and the grass and organic thatch creates a little bit of a resistant layer, and then so the water kind of falls over it and cuts underneath, and then eventually, right, you get this kind of cantilever, and this falls in. Okay. The other kind is called spring sapping, where the water is seeping out of a spring or seep in the wall, and then it's cutting down from there, and that's called spring sapping, and then the blocks above it will fall. And we'll see some of that in other places. We don't really see that here. We definitely see some undercutting, and then just these little micro slumps as it bites back. And the reason I bring that up is because if you look out, look at the terraces way out in the distance, how flat they are, and all of the valleys kind of like go back up into there. The streams here, the tributaries, are eating back into this grassland. And you're going to see as we drive today, we're going to be, after we go through Norbeck Pass, we're going to be up on the edge. And the road actually has places where the road's been completely rebuilt because the edge of the prairie is being cut into as it's slumping down into the valley below. Okay? So this is, in geomorphology, we call that dynamic equilibrium. Change is constant. So this is constantly changing. And eventually, like you said, eventually this will be eroded away. The Badlands will be eroded away. And you said 500,000 years based on 1 inch per year. Last thing is, notice how everything is so neatly layered here. You can kind of make out really pretty clear layering with the colors and the different textures. As we're leaving here and we go down over Cedar Pass, take a look at the stuff to the right of us. Okay, so we're going to bend from here. We're going to go around and bend down, and we're going to stop where so we all have to take our shirts off and pose like those guys. Where those guys, the shirtless dudes were stopped, we're going to stop there and do a little overlook, but then we'll go down. Keep your eyes to the right, and you're going to notice something about the layers. Okay? Yeah, it's pretty cool. And it isn't coincidental.
Yeah. One other thing, Mitch has been just chomping at the bit. Do you see anything else interesting?
Is it shale? Is it the shale?
No. What do you see here, Mitch, that you've been worried about recently? not talking about because I was told not to until we were all together. You see,
There's a little bit over there. But...
well, look through here.
Do you want to wait until we get to the place before Dillon Pass? Because it's
There's a
really
that's
well,
the really good one.
really
there.
well pronounced.
You can see it pretty good here, like out through there and up here. But we can wait.
We're kind of looking into the face of one right
It's
there.
that fin right there,
I'm gonna build the anticipation some more.
which has been going nuts.
Just
Wanting to know.
actually,
And that ridge line out there, you can see it coming right through.
Yeah.
There's one right there. There's a whole bunch. When we were walking along the boardwalk, you can see a bunch of them.
yeah, maybe let's go to where we can see a really clear one. 'Cause, like these are
That's
not
the fin. Look, but you can see it coming down.
you and I can.
Yeah.
But I want to, if they could look like right into it.
There's a really obvious one over here. Okay, you guys hold up. Come on back this way.
I'll run interference while you.
So do you all see these like vertical features periodically? That one's pretty good because it's really obvious. There's one sticking out here, and you can see over there, there's like a line of what looks like slightly more resistant material, and it's vertical, right? Like if you see the tallest peak in this kind of wall over here, go down into that little saddle, and then climb up to the middle of the next one, and then it's like right kind of to the left of center there, like that kind of vertical thing. Those are dikes, right? But they're not igneous here. So is everybody familiar with the term dike, right? Intrusion that cuts through layering, basically. These are sedimentary dikes, right? So during deposition, you get these really fluid saturated layers, and they sometimes get buried relatively quickly, and the layering above it continues to collect above that fluid saturated layer, and eventually the weight becomes too much for the fluid layer, and a fracture develops, and that kind of fluid supported sediment squeezes up through the fracture and forms these somewhat more resistant sedimentary layers. But the vertical resistant stuff is more sedimentary rock. It's just been squeezed up through vertical fractures during gradual deposition.
Okay, this is and so you guys get that? Everybody get that? You have a very porous rock that has a lot of water, and it's covered with a seal layer that is very clay rich, and you keep adding pressure, and then it pops up a fracture.
Water's incompressible, right? So
yeah, so the water wants to squeeze up, and it takes the sediment with it. But the sediment that it's taking with it, let's drop a few of us down. The sediment that it's taking with it is very often, think about around here a lot, it's this kind of dry land, wind-blown sediments, and every once in a while there's a big pulse of a lot of sediment that's very uniform, very porous, set down very quickly. Any idea why that might happen?
volcanic ash?
Yeah, volcanic ash deposits. That's the, what did you call it? The Rocky Ford? Yeah, so there are these ash layers that have, they're really high silica, they're rhyolitic in composition, so they're laid down and very porous. So they're full of water, and then you get new sediment laid on top. Then that ash layer gets squeezed through the fractures. What happens to rhyolitic volcanic ash when it's weathered? Anybody know what it alters to?
Clay?
What kind of clay? So does a grain size. What kind of clay? What? starts with a B. What?
Oh,
Bentonite. Yeah, bentonite. And what's unique about bentonite?
Champions.
Yeah, it swells. So think about if you're squeezing these ashes up into these fractures, and then it is altering to bentonite, and that bentonite has a high shrink swell capacity, what do you think happens along those fractures? Shrink and swell and preferential erosion. So this is a really nice one. You see that where it's like discolored along there? This one is a little bit different. That's probably, yeah, that's a more resistant one. So chemically that's something a little bit different. Also, you can sometimes correlate them. So you see that one in that surface, and see it over here? It actually extends across. So you can connect those two. All right, there's a couple overlooks where it's really, really beautifully expressed, and you'll actually see it running for, or, tens to hundreds of yards, or meters, I should say.
So have you been here when you were younger and it was very high, or is it not easy to see?
It's not changing.
Yeah, 1 inch per year. Yeah, it is.
And somebody made the comment in my van about topographic maps. It's not changing that rapidly.
I just feel like seeing all this stuff cooling at the bottom is wow, it seems rapid.
Well, Dr. Burkhart at Slippery Rock, this is where he specializes in the White River Badlands. That's what this is called, and he did a study very recently. He presented some results looking at the deposition rates behind some of these slump blocks. And when we see some obvious ones, I'll show you. But basically what's happened is you get these slumps of the grasslands. So it's very clearly the same. So you have grass and then it drops down the slope like that. So you can very clearly tie the two together. And then they've been looking along the back side to see how much sediment is now following along to try to get some of those erosion rates and the infills around those new features. And it's really, in geologic time, it's really rapid, but in our time now, you won't see that. Think about like a geomorphic or a topographic map is 20-foot contours. How many years would have to pass before you'd have to change the contours?
Right. And you look at this stuff, what would this look like on a topographic map? You wouldn't see, the things we're noticing, you wouldn't see on a topographic map because that's 20 feet tall or less, right? So you're not going to make out a lot of these things. Unless it's just happens to be right at the even border.
Cool. Okay.
Did you say it was in rhyolite?
Yeah, it's rhyolitic. It's rhyolitic. So it's just, so when I say rhyolitic, you guys know the the igneous classification scheme.
Which one?
Are you asking inches of extra? Obviously, it's
Keep it simple. I can see the shape you're drawing. Do the simple one.
Yeah. Yeah, this is this is a really, really simple, that's an F. So what's APH? Aphanitic, phaneritic. So fine crystalline, coarse crystalline. F, felsic, I, mafic, ultramafic. Good. Okay, what goes here?
Komatiite.
Awesome. Komatiite. What goes here?
Gabbro.
Nope. Ultramafic.
Olivine.
Nope.
Which makes what rock? P.
Peridotite.
Komatiite, but not peridotite.
Because I get really excited about
Yeah, he gets so excited about the
komatiite rafts.
He gets so excited.
Okay, now Gabbro is here. Okay, what goes here? Basalt. Andesite. Good. I knew this was going to give you trouble.
Oh no, it's like it's
Diorite. Good. Yeah, diorite. Okay, down here. Granite.
Basalt.
Nice one, John.
You made him so proud of it, ruined it 2 minutes later.
It's almost like you planned that. My brain broke a little.
He's like set the bar so high.
I know. Comadiite and then.
You build yourself up just to break
Yeah.
yourself down.
And disappointed him
Another
again.
disappointment.
Okay, so when I say a rhyolitic, that just means chemically it's in here. So it's volcanic, it's felsic, and because you can't, like pure silica, you're not going to turn into bentonite. Obviously there's other stuff in it that are going to help it alter to that. But that when I say rhyolitic or granitic, that just means chemically we're over in here. And you know, basaltic is, again, chemically, it's just an easier way to say the ratio, yeah, the chemistry. Okay. And what are some of the signatures they can use to say, all right, this eruption can be tied to that volcano in Oregon or that volcano in Utah or Yellowstone? What are they looking for?
Well, the style of volcanism is related to the tectonic setting. So if you are looking for something subduction related, it might cause a more intermediate or towards felsic magmatism. Is that kind of what you're looking at?
No,
Or
like specifically chemically, what would be a really good signature to say, okay, this ash comes from that deposit?
Coloration really helps a lot, if that's what you're looking for, like a quick visual sense. If you're dealing with more mafic magmatism, you've got enrichment towards magnesium and iron and so forth, manganese. If you have a more felsic eruptive style, you've got more silica enrichment, you've got potassium, lighter colored things. And you can see some of that in the coloration. Sometimes the rate of erosion matters. The mafic stuff weathers more quickly, it turns out, and the more felsic magmatism tends to be a little bit more resistant.
What about timing?
In terms of tectonic events?
No, like
Grain cells?
Zircons?
They
You can date zircon. So felsic magmatism often has accessory minerals that include apatite and zircon. Both of those can be reliably dated by geochronologic methods. Mafic magmatism is more challenging. You can sometimes find some mafic minerals to date, but they provide less reliable ages. You can find zircons in mafic materials, but they're really rare. So you'd have to process like 5 times as much rock, and you still might not find anything. Granites and rhyolites always have zircons and apatites. So if it's felsic, you can get an age for it. And I like talking about this in my labs because it's like the thing I like to do the most. But guess how much it costs to collect an age? Like, I'm assuming you already have a processed sample. Guess how much it costs to collect an age for a zircon grain?
Isn't it like $800?
No, less.
$100.
Less. Less.
$1.
More.
$5.
$2 per grain. If you go to Arizona. If you're at the shrimp, it's a little more expensive. It's like $15 per grain. But yeah, if you go to the Lasercron Center in Arizona, it's like $2 per grain. So there's some other lab
how many
costs.
grains are you doing?
It depends. If you're doing an igneous rock at the Lasercron Center, maybe like 20. If you're using the shrimp, more like 10. If you're doing a sandstone, several hundred.
But that's kind of my point, is that you can look chemically at, you know, ratios of different elements as signatures to compare magma sources to these deposits, but you can also you can nail it down to plus or minus.
Oh, geez, yeah. 500,000 years if you're using the shrimp.
So if there's an eruption in Oregon that was at, you know, 37.5 0.52 million years, plus or minus 10,000, and you have an ash here that dates exactly the same, and it chemically looks about the same. That's how they're tracing it over these great distances.
And ash has zircon in it. I knew a grad student that dated ash deposits in Texas by zircons.
Yeah.
So.
And so the other thing, remember, is that the ash doesn't have to be dropped aerially. I mean, it is, right, ashfall deposits, but it also falls in other places, and then streams carry it and deposit it. So there's, multiple sources of ash. It's the same ash, it's just, so you have to be a little bit careful about, layering and things like that.
And to speak to your point of the precision, the granites we dated in Siberia, they were Cretaceous, but they were within 300,000 years of the crystallization age, which is crazy.
Wow.
Yeah, super high precision.
And that was, what, 15 years ago?
Oh yeah, that's a good point.
Yeah, so and even with that, it's probably half that.
Standards, yeah. Yeah, it's wild.
Okay, questions? And that was a lot, but hopefully. So the part of this is to just give you a little something to grab onto for classes that you have already had, but also we're kind of fire hosing information at you. So when you go to class in the fall, Dr. Straffen will say, bentonite, and you'll be like, oh, remember that?
Oh, we got that
looking
tonight
at it.
nailed down.
Oh, okay.
Yeah. Yeah.
That guy.
Okay, so we're gonna stop at the shirts off spot and take a look.
Yes. Oh yeah, no, there's I noticed it when we were driving yesterday. There's a prominent volcanic ash layer that helps you find your place in this particular. That's not the big one. Isn't what this is from, because this is too old. This is all brule. And I can't remember the rock ash is, I think, at the upper end of the brule before the shard. Okay. So, but there were periodic eruptions that deposited thin layers of ash periodically.
I think I got some pretty clay.
Yeah, it was stuck on the clay. So you have a relatively rapid, like picture Australia, but the environment is kind of fluctuating. The clays in the area. Oh yeah, that's a really good one.
This one, that's extra.
In here, look at this one. That vertical.
Oh, wait, are those two connected?
Yeah. Ooh, very cool. How long you play you have this really saturated clay layer, and if it stays and then you just gradually add more and more weight on top of it, and it seals it off because the water can't move through other clay that's impermeable, and you just keep compressing it, you have like this toothpastey gunk. Yeah, the pressure builds up, and it just like squirts up
After a
through
real
the
quick
pressure.
roadside stop, then we're gonna go to the visitor center.
Squirting up like a toothpaste bottle.
It comes up through a fraction. Yeah, and it's because of stress, right? It's the same thing, where if you pinch my fingers, it's going to do that. That's the
that a jackalope?
compressive direction. Oh, it's a baby jackalope.
They are.
I want to pet him. He is so
No, they're not. They're not. Yeah, no,
Catch him. Bring him in the land. This thing get crazy close. Yeah.
He knew I was a rabbit whisperer.
Yeah.
And I think for it's like a bad thing I feel bad.
My landlord, he's like, I said one rabbit, and I was like,
I don't want to